Rotating a square metal plate. A square metal plate 0.18 meters on each side is pivoted about an axis through point O at its center and perpendicular to the plate. You can see in the figure. Calculate the net torque about this axis due to the three forces shown in the figure if the magnitudes of the forces are F1 equals 18 newtons, F2 equals 26 newtons, and F3 equals 14 newtons. The plate and all forces are in the plane of the page. Okay, so we set up our coordinate axes x, y, and z like this, and we're looking at the perpendicular distance for each force. So for F1, you can see that the perpendicular distance will be R1 perpendicular. So we have the position vector of the application point of the force with respect to the pivot, and then we find the perpendicular distance. So how much is the perpendicular distance in this case? So R1 perpendicular is basically the side length 0.180 meters divided by 2, which will give us 0.09 meters. And the torque due to this force will be the position vector of the application point with respect to the pivot point, R1, cross product with the force F1. So R1 is basically this vector here. This is the position vector, and you can see that it has two components, 0.09 I hat and 0.09 j hat. So we have 0.09 I hat plus 0.09 j hat cross product with the force. The force is in a minus j hat direction, and therefore we can write here minus 18 j hat. Now you can see that j hat cross j hat will be 0, so this is actually equal to 0.09 minus 0.09 times 18. So I hat cross j hat is k hat, so I hat, j hat, k hat, cyclic permutations in the clockwise direction. You can see that this is the positive direction. So I hat cross j hat is k hat, so it's minus k hat here. So this is going to give us minus 1.62 Newton meters in k hat direction. Or you can say that it's the perpendicular distance 0.09 multiplied with the magnitude of the force 18, but then we have to use the right hand rule to find the direction of the force. So your four fingers point in the direction of R1 perpendicular, curl them towards F1, and the thumb points into the page, which means it's in minus k hat direction. So you can see here, this is our R1 perpendicular, and this is our F1. So perpendicular, of course, you cannot see because it's hidden in the arrow. So we can see that it's going to be pointing in the minus k hat direction. All right, now let's move on to the other forces. Force F2 is applied here. It has a position vector R2 with respect to the pivot point O, and it has a perpendicular distance also equal to 0.09 meters. So we can see that R2 perpendicular here is also equal to 1.80, the side length divided by 2, no, not 1.80, it's 0.180 divided by 2, which is 0.09 meters. And the torque due to this force is basically R2 cross F2. Now, what is the position vector of the application point here? You can see that it is in minus 0.09 I hat direction and plus 0.09 j hat direction. So it's minus 0.09 I hat plus 0.09 j hat cross with F2. Well, F2 magnitude was 26 newtons, so it is 26, and it is also in minus j hat direction. You can see here it's in minus j hat direction. So j hat cross j hat is 0, so I hat cross j hat will give us k hat, and there are two minus signs, so we will obtain 2.34 Newton meters in k hat direction. Now let's move on to the third force. Third force application point has a position vector R3 with respect to the pivot point, which is at minus 0.09 j hat plus 0.09 I hat. So those are the components. So we can see that the torque 3, let's do that here, torque 3 will be equal to R3 cross F3. The position vector of the application point of the force is 0.09 I hat minus 0.09 j hat, and cross product with F3. Now we have to be careful. F3 makes an angle 45 degrees with respect to the horizontal, with respect to the vertical axis here. So it will have a component F3 cosine 45 in j hat direction, and it will have a component F3 sine 45 in I hat direction. And F3 magnitude was 14 newtons. So we can say that this is 14 cosine 45 in I hat direction plus 14 sine 45. Now let's take a look at this. F3 is actually here. It's cosine 45 j hat direction. So this is going to be sine 45 I hat direction and cosine 45 j hat direction. So this will give us 0.09 square root 2 times 14 in k hat direction. So we will encounter I hat cross j hat, which is k hat, and then we will encounter minus j hat cross with I hat, which will be in minus k hat direction. So these two will give us our final answer here. So another way to see that is we need to look at the perpendicular distance between the application point and the pivot point here. R3 perpendicular is going to be equal to the length of the diagonal 1.80 square root 2 of the square divided by 2. So you can see that this is actually 0.09 square root 2. So we have to multiply 0.09 square root 2 with 14. And using the right hand rule, you can see that if you point from the pivot point to the application point using your right hand and curl your forefingers towards F3. Your thumb points out of the page in plus k hat direction. So this gives us as the final answer 1.26 square root 2 Newton meters in k hat direction. Now we can calculate the net torque acting on this square. The net torque will be torque due to the first force plus torque due to the second force plus torque due to the third force. And this will be equal to, the first force had a torque minus 1.62. So minus 1.62. The second force 2.34. And the third force 1.26 square root 2 in k hat direction. So this gives us 2.50 Newton meters in k hat direction. So the net force, the net torque is basically pointing out of the page. Okay. So we have calculated the net torque acting on a square metal plate, which is under the influence of three forces you can see here, F1, F2, and F3. So the task of calculating the torque is basically finding the perpendicular distance between the application point of the force and the pivot point. So you can see that for F1, the perpendicular distance is basically R1 perpendicular. For F2, it's R2 perpendicular. And for F3, F3 is already perpendicular, so it's R3 magnitude will be the perpendicular distance. Or you can write the R1 and F1 vectors explicitly. R1 vector has a component the side length divided by 2 in I hat and the side length divided by 2 in j hat. So crossed with F1, F1 is in minus j hat direction, minus 18 j hat. I hat cross, you can use these cyclic permutations. I hat cross j hat is k hat, but j hat cross j hat is 0, so that gives us our final answer. So the task for F2 is similar, only the position vector now has a negative x component, minus 0.09 I hat plus 0.09 j hat. So it's also equal to the perpendicular distance R2 perpendicular multiplied with the magnitude F2, and then you can find the direction using the right hand rule. Point towards the application point of the force, curl your forefingers towards F2, your thumb points out of the page in plus k hat direction. For F3, we have found that if we do this explicitly writing these vectors, R3 vector, the position vector of the application point, has a negative y component but positive x component. And F3, if you carry this force here, basically it has F3 cosine 45 j hat, F3 sine 45 I hat, x component and y component. Or we can do this explicitly. Instead of doing it this way, the perpendicular distance between the application point and the pivot point is basically the magnitude of this vector R3, which is the side length square root 2 divided by 2. So we multiply it with the magnitude of this force and then use the right hand rule. Point towards the application point with the right hand, curl your fingers towards F3, the thumb points out of the page. So it's in plus k hat direction. And we add up all of these contributions and we get our final answer to be 2.50 Newton meters is the unit of torque in plus k hat direction.